The moon, long thought to be a silent, inactive rock, is now revealing secrets that could change everything we know about our closest celestial neighbor. Renowned physicist Michio Kaku has issued a warning after NASA detected a mysterious seismic signal deep within the moon's core. This discovery challenges decades of assumptions and hints at dynamic processes that might even impact Earth over geological timescales. Today, we explore what this seismic activity means for lunar science, future missions, and our understanding of planetary evolution. The moon's hidden activity revealed. For decades, scientists believed the moon was geologically dead, its core solidifying and cooling quietly like a dying ember in space. But recent data from NASA's lunar sensors have detected unexpected seismic pulses emanating from deep within the moon's interior, challenging everything we thought we knew about our celestial companion. These signals suggest the moon's core is not just passively cooling, but undergoing significant changes that could reshape our understanding of lunar evolution. Physicist Michio Kaku has highlighted these findings in recent lectures, warning that the moon's internal activity could have long-term effects on its structure and even Earth's environment over geological timescales. This seismic activity challenges the traditional view of the moon as a static, inert body that finished its geological story billions of years ago. The discovery represents a paradigm shift in lunar science, forcing researchers to reconsider fundamental assumptions about how small planetary bodies evolve and die in our solar system. Inside the moon's dynamic core structure. The moon's internal structure resembles a miniature version of Earth's, with a solid inner core surrounded by a partially molten outer core that scientists are now discovering remains more active than previously thought. New analyses estimate the inner core's radius at approximately 240 kilometers, primarily composed of iron and nickel, enveloped by a fluid outer core extending roughly 350 kilometers from the moon's center. Geological evidence from lunar rocks brought back by Apollo missions shows the moon once possessed a magnetic field generated by its core, similar to Earth's protective magnetosphere. This ancient magnetic field, which existed billions of years ago, gradually faded as the core cooled and solidified. However, recent seismic data suggests the core might still be active in subtle but measurable ways. The core's structure includes a partial melt layer at the base of the lunar mantle, approximately 150 kilometers thick, which sits above the liquid outer core. This complex internal architecture indicates that the moon's interior remains more dynamic than the simple cooling model previously accepted by planetary scientists. Apollo's legacy and modern seismic discoveries. NASA's Apollo missions first placed seismometers on the moon between 1969 and 1977, with the Apollo 11 passive seismic experiment marking humanity's first attempt to listen to another world's internal activity. These instruments detected moonquakes and revealed some internal activity, recording about 100 to 200 meteorite impacts during their operational lifetime and detecting several categories of seismic events. However, the resolution of those 1970s instruments was limited by the technology available at the time. The Apollo seismometers operated until September 1977, providing valuable but incomplete data about lunar seismic activity. Now, with advanced sensors and modern analysis techniques, scientists are uncovering new categories of seismic events that were previously undetectable. These include deep moonquakes caused by tidal forces with Earth, shallow quakes with tectonic origins, and thermal quakes caused by extreme temperature fluctuations between lunar day and night. The new data suggests the moon's interior is more dynamic than once thought, with ongoing processes that continue to shape its internal structure even today. The shrinking moon theory and tectonic activity. One of the most intriguing hypotheses emerging from recent research is that the moon is slowly shrinking as its core continues to cool and solidify over geological time. This gradual contraction causes stress in the brittle lunar crust, leading to the formation of tectonic ridges, fault lines, and surface scarps that are surprisingly young in geological terms. Recent studies have identified hundreds of previously unknown ridges on the moon's surface, some of which may have formed as recently as 200 million years ago, a blink of an eye in geological terms. Using advanced mapping techniques and crater counting methods, scientists determined that these small ridges are younger than other features in their surroundings, meaning the moon's crust is still shifting and evolving today. This slow contraction and associated seismic activity could explain the mysterious seismic pulses detected recently, suggesting the moon is still adjusting internally as it continues its billion-year cooling process. The discovery challenges the long-standing belief that the moon became geologically dormant billions of years ago, and suggests that internal forces are still shaping its surface in measurable ways.
Earth-Moon gravitational dance and climate implications.
The implications of the moon's internal activity extend far beyond lunar science, potentially affecting Earth's long-term climate stability and orbital dynamics. The moon's gravitational influence stabilizes Earth's axial tilt at 23.5 degrees, which regulates our seasons and prevents chaotic climate swings that would make complex life difficult to sustain. Changes in the moon's mass distribution due to core activity and internal restructuring could subtly affect this crucial gravitational relationship over timescales of millions of years. While these effects are not immediate or catastrophic, they could influence Earth's climate cycles, tidal patterns, and even the Milankovitch cycles that govern ice ages over geological epochs. Michio Kaku has emphasized that the moon acts like a cosmic stabilizer, preventing Earth from wobbling chaotically like other planets of similar size. This stability has allowed for the slow, steady development of ecosystems and eventually human civilization. The moon's gravitational pull creates not just ocean tides, but also slight bulges in Earth's crust, generating heat through friction that contributes to our planet's internal warmth and geologic activity.
Next-generation lunar seismic monitoring.
NASA is preparing to deploy revolutionary new seismic instruments on the moon as part of upcoming Artemis missions, representing a quantum leap forward in our ability to monitor lunar internal activity. The Farside Seismic Suite, scheduled to land in Schrödinger Basin around 2026, will be the first seismic station placed on the moon's far side since the Apollo era. These next-generation seismometers will be approximately 30 times more sensitive than Apollo-era equipment, capable of detecting ground motions smaller than a single hydrogen atom. The Very Broadband Seismometer, originally designed for Mars InSight mission, represents the most sensitive seismometer ever built for space exploration. Additionally, the Lunar Environment Monitoring Station will establish a long-duration seismic station near the South Pole, where NASA's Artemis missions plan to build a permanent human presence. Unlike Apollo instruments that operated for limited periods, these new systems are designed to continuously monitor lunar seismic activity for months or even years, providing unprecedented insights into the moon's internal dynamics.
AI revolutionizes Apollo-era data analysis.
Artificial intelligence is playing, a crucial role in revolutionizing our understanding of lunar seismic activity by analyzing decades-old Apollo data with unprecedented precision. It's like machine learning algorithms are detecting patterns and anomalies in the original seismic recordings that human analysts missed or dismissed as noise during the 1970s analysis. These sophisticated AI systems can distinguish between genuine lunar activity and instrument artifacts with remarkable accuracy, flagging seismic events that didn't fit expected patterns and were often filtered out as measurement errors decades ago. NASA scientists describe this process as revolutionary, comparing it to having a conversation with someone for 50 years and suddenly realizing you've been missing half of what they've been saying. The AI analysis has revealed entire categories of seismic events occurring beneath the lunar surface that were completely missed by previous analysis techniques. These aren't just minor tremors but signatures of complex processes happening in the moon's core that provide new insights into its internal structure and ongoing geological activity. This technological breakthrough is helping scientists reconstruct a completely new picture of the moon's internal dynamics and the seismic pulse that has drawn Michio Kaku's attention.
Lunar exploration safety and future mission planning.
So, the discovery of ongoing seismic activity on the moon, well, it really raises some critical safety considerations for future lunar exploration and colonization efforts. Human missions and those mining operations planned near the lunar South Pole, they've got to carefully consider the risks posed by tectonic activity and potential moonquakes that could damage habitats or endanger astronauts. Understanding fault zones and stress patterns is just essential if we want to ensure the safety and stability of lunar habitats and infrastructure. Unlike Earth, the moon's crust doesn't have water circulation to heal cracks naturally, so once we fracture its brittle surface through mining or construction, those fractures could stick around and potentially trigger even larger seismic events. NASA's upcoming seismic networks will be absolutely vital for mapping these geological hazards and guiding mission planning for the Artemis program. The lunar regolith, which is that layer of loose material covering the moon's surface, actually sits atop a pretty complex network of faults and stress zones that could be disturbed by human activity. Future lunar bases are going to be completely dependent on their structural integrity, making seismic monitoring crucial for astronaut safety, and a habitat breach caused by unexpected seismic activity could be catastrophic, exposing crew members to the vacuum of space with very little warning or opportunity for evacuation.
A rare cosmic window for scientific discovery.
Michio Kaku emphasizes that humanity exists in a rare cosmic window, a fleeting moment in astronomical time when the moon's internal activity is still detectable before it eventually ceases forever. In another billion years or so, the moon's core may freeze solid completely, ending the geological processes we can observe today. This unique opportunity allows scientists to study planetary evolution processes that happen over billions of years, providing insights that, honestly, can't be obtained any other way. The moon is pretty much giving us a live demonstration of how small planetary bodies evolve and eventually become geologically inactive, serving as a sort of natural laboratory for understanding planetary death. Insights gained from studying the moon's core activity can inform our understanding of other rocky bodies in the solar system and beyond, including potentially habitable exoplanets. By watching the moon transition from a molten core to a solid one, scientists gain crucial insights into how different-sized worlds evolve, whether they can maintain protective magnetic fields, and their potential for supporting life. Kaku explains that we're incredibly fortunate to exist at exactly the right moment to witness the final chapters of the moon's geological story.
The moon as a key to planetary evolution.
The moon's seismic signals represent far more than just scientific curiosities. They're actually fundamental keys to understanding planetary life cycles throughout the universe. As the moon's core continues to cool and solidify, it offers researchers an unprecedented live demonstration of how small planetary bodies evolve and eventually die, providing crucial data for planetary science models. This knowledge is particularly vital as humanity prepares to return to the moon and establish a permanent presence there. Understanding the moon's internal processes helps scientists identify potentially habitable exoplanets and predict how their geological evolution might affect their ability to support life over billions of years. The moon serves as an intermediate step in planetary development, larger than asteroids but smaller than Earth-like planets, giving us really important insights into how different-sized worlds evolve. By studying how the moon's core solidifies and loses its magnetic field, scientists can develop models that predict how long smaller rocky exoplanets might maintain their protective magnetic shields. Michio Kaku's warning reminds us that the moon still holds secrets that could totally reshape our understanding of planetary science, Earth's future, and our place in the cosmic neighborhood. The moon is no longer the silent, dead rock we once thought it was. Thanks to new seismic discoveries and Michio Kaku's warnings, we now know it's a dynamic world with an active interior that could even influence Earth itself. As we prepare to return and explore further, understanding these internal processes is more important than ever before. Stay tuned for more updates on lunar science and the future of space exploration. Thanks for watching Stellar Tech, and don't forget to subscribe for more cosmic insights. Fresh observations are now shedding new light on 3I/Atlas, the massive interstellar visitor that's been puzzling astronomers since its discovery. What started as excitement over finding our third interstellar object has transformed into something far more intriguing and honestly controversial. Recent data analysis reveals patterns that just shouldn't exist in natural objects. Orbital characteristics so precise they seem almost intentional. Professor Avi Loeb and other researchers are asking uncomfortable questions. What if 3I/Atlas isn't just a comet? What if it's something designed to study us while appearing completely natural?
Fresh observations reveal mysteries.
Recent months of intensive observation have transformed 3I/Atlas from an exciting discovery into astronomy's most controversial object since Oumuamua. Dr. Robert Warwick from the University of Hawaii, who led the discovery team, admits that new data has revealed characteristics that challenge our understanding of natural interstellar objects. The object's behavior patterns have proven increasingly difficult to explain through conventional comet models. Advanced spectroscopic analysis by the European Southern Observatory shows surface composition anomalies that don't match any known class of solar system bodies. Most puzzling is the object's thermal signature, or rather the lack thereof. Despite approaching within 0.7 AU of the Sun, 3I/Atlas shows minimal heat emission and no detectable outgassing. Dr. Michelle Bannister from the University of Canterbury noted that objects this size should be streaming gas and dust as they heat up, but we're seeing virtually nothing. The observations have split the astronomical community between those who believe there must be a natural explanation, and others who are beginning to consider more exotic possibilities. NASA's Deep Space Network continues tracking the object, but each new measurement seems to deepen rather than resolve the mystery.
The scientific debate.
The astronomical community finds itself divided over 3I/Atlas, with heated debates emerging at conferences and in scientific journals. Dr. Alan Fitzsimmons from Queen's University Belfast leads the conventional camp, arguing that extraordinary claims require extraordinary evidence, and we haven't reached that threshold yet. His team maintains that unusual properties can be explained by exotic but natural compositions, possibly involving nitrogen ice or other materials rare in our solar system. However, a growing faction of researchers questions this dismissive approach. Dr. Daryl Seligman from the University of Chicago, who previously proposed natural explanations for Oumuamua, admits that 3I/Atlas presents characteristics that are harder to reconcile with known natural processes. The debate intensified when thermal modeling by Dr. Marco Michelli from the European Space Agency revealed that the object's temperature distribution doesn't match any known natural body. Spectroscopic measurements show absorption lines that appear artificially narrow, suggesting either unknown physics or manufactured materials. Dr. Sarah Seeger from MIT cautioned against rushing to conclusions, but acknowledged that we may need to expand our definitions of what constitutes natural phenomena in interstellar space. The scientific method demands skepticism, yet the mounting anomalies are forcing astronomers to confront uncomfortable possibilities.
The artificial origin hypothesis.
Professor Abraham Loeb, former chair of Harvard's astronomy department, has emerged as the most vocal proponent of an artificial origin for 3I/Atlas. Building on his controversial Oumuamua research, Loeb argues that the object displays technological signatures that suggest intelligent design rather than natural formation. His analysis focuses on the object's perfect orbital mechanics, unusual surface properties, and lack of expected comet behavior. Loeb's calculations suggest that 3I/Atlas's trajectory shows statistical precision that would be virtually impossible to achieve naturally. The object's approach vector, timing, and encounters with multiple planets create what he calls a reconnaissance pattern consistent with systematic exploration. In his recent paper submitted to Astrophysical Journal Letters, Loeb proposes that 3I/Atlas could be a probe designed to study our solar system while maintaining the appearance of a natural comet. His hypothesis suggests that advanced civilizations might use such camouflaged objects to observe other star systems without detection. Critics argue that Loeb is making extraordinary leaps from limited data, but his mathematical analysis of the object's properties continues to gain attention from researchers who find conventional explanations increasingly inadequate for the mounting anomalies.
Unusual detection pattern.
The circumstances surrounding 3I/Atlas's discovery reveal troubling patterns that suggest possible stealth capabilities. Dr. Larry Deneau from the Atlas Asteroid Survey noted that the object should have been detected 18 months earlier based on its size and trajectory, yet it remained invisible to all automated survey systems until July 2025. The delayed detection becomes even more suspicious when considering the object's approach vector from the constellation Lynx, a region of sky that multiple survey telescopes regularly monitor. Orbital reconstruction by Dr. Davide Farnochia at NASA's Jet Propulsion Laboratory reveals that 3I/Atlas entered the outer solar system in January 2024, but somehow avoided detection despite passing through well-monitored space. The object's approach direction created additional observational challenges, as it remained positioned in areas of sky that were difficult to observe from Earth-based telescopes for extended periods. Dr. Catalina Donovan from the Linear program admitted that, Objects this bright should have triggered multiple detection systems, but somehow it remained hidden until practically on top of us. This pattern of avoiding detection until the last possible moment really raises questions about whether the concealment was accidental or intentional, adding weight to theories about possible artificial intelligence guiding the object's approach.
Suspicious orbital characteristics.
3. I-Atlas's orbital mechanics present statistical anomalies that challenge natural origin theories through their mathematical precision. Dr. Fatih Namouni from Côte d'Azur Observatory calculated that the object's perfect alignment with the ecliptic plane has only a 0.2% probability of occurring naturally for an interstellar visitor. More striking are the object's sequential close encounters with Venus, Mars, and Jupiter, which orbital dynamicist Dr. Mattia Galeazzo from the University of Vienna determined has only a 0.005% probability of happening by chance. The precision of these encounters suggests either extraordinary coincidence or deliberate trajectory planning. 3. I-Atlas will pass within optimal observation range of each planet, maximizing potential data collection opportunities about their atmospheric compositions, magnetic fields, and moons. Dr. Alessandro Morbidelli from the Observatory of the Côte d'Azur noted that the trajectory looks almost designed to provide comprehensive reconnaissance of our solar system's major worlds. The object's velocity profile also shows subtle variations that correlate with planetary encounters, suggesting possible course corrections that natural objects shouldn't exhibit. Statistical analysis by Dr. Renu Malhotra from the University of Arizona concluded that the combined probability of all observed orbital characteristics occurring naturally is less than 0.001%, forcing serious consideration of artificial guidance systems.
The hidden approach strategy.
3. I-Atlas's approach timing demonstrates what researchers are calling strategic concealment that maximizes the object's ability to study Earth while minimizing detection opportunities. Dr. Paul Wiegert from Western University discovered that the object's perihelion passage in December 2025 coincides with Earth's position in its orbit, creating an observational blind spot that has a 7% probability of occurring randomly. During this critical period, 3I-Atlas will be positioned directly behind the Sun from Earth's perspective, making detailed observation extremely difficult while allowing the object unobstructed views of our planet. Celestial mechanics expert Dr. Kleomenis Tsiganis from Aristotle University noted that this timing allows the object to study Earth's electromagnetic emissions, atmospheric composition, and artificial satellite networks without interference from ground-based observations. The approach strategy becomes more sophisticated when considering that 3Y-Atlas will emerge from behind the Sun in January 2026 at optimal angles for both radio telescope detection and deep space communication. Dr. Seth Shostak from the SETI Institute acknowledged that if we were designing a reconnaissance mission to study an inhabited planet, this trajectory would be nearly optimal. The implications are unsettling. 3I-Atlas appears positioned to conduct comprehensive Earth observation while maintaining plausible deniability as a natural comet.
Scientific opposition and evidence.
Despite mounting anomalies, many astronomers maintain strong skepticism about artificial origin theories for 3I/Atlas. Dr. Alan Harris from the German Aerospace Center argues that size estimates remain uncertain, and unusual properties don't automatically imply artificial construction. His team's thermal modeling suggests the object could be significantly smaller than initial estimates, potentially explaining some observed anomalies through natural processes. Dr. Vishnu Reddy from the University of Arizona emphasizes that interstellar objects should be expected to show unusual properties, since they formed in different stellar environments with unknown conditions. Counter-evidence includes spectroscopic data showing absorption features consistent with water ice and rocky materials, though critics note these signatures could be engineered camouflage. Dr. Julie Castillo-Roges from NASA's Jet Propulsion Laboratory points out that we've only studied 3 interstellar objects, making it premature to define what constitutes normal behavior. The scientific opposition maintains that natural explanations involving exotic ices, unusual mineral compositions, or unknown formation mechanisms remain more plausible than extraterrestrial technology. Dr. Bonnie Barati from JPL advocates for continued observation rather than speculation, arguing that patience and data collection will eventually reveal natural explanations for these apparent anomalies. However, each new observation seems to strengthen rather than weaken the case for artificial origins.
Ancient origins and anomalous behavior.
Age analysis of 3I/Atlas reveals characteristics that seem to defy the natural aging process expected for interstellar objects. Dr. Grigory Fedoretz from Queen's University Belfast estimates the object's age at over 7 billion years based on surface composition analysis, making it older than our solar system yet showing no signs of expected cosmic weathering. Objects drifting through interstellar space for such periods should exhibit significant cosmic ray damage, micrometeorite scarring and surface oxidation, yet 3I/Atlas appears remarkably pristine. Most puzzling is the complete absence of a comet tail despite the object's approach to within 0.7 astronomical units of the Sun. Dr. Matthew Knight from the University of Maryland noted that any object containing even trace amounts of volatiles should be outgassing visibly by now, but we're seeing nothing. Structural analysis by Dr. Jean-Baptiste Vincent from the German Aerospace Center reveals density variations that are inconsistent with typical water ice spectra, suggesting either unknown materials or artificial construction. The object's rotation period of exactly 12 hours also raises suspicions, as natural bodies typically show irregular rotation rates due to impact history and gravitational perturbations. These ancient origins combined with anomalous behavior patterns continue to challenge conventional explanations.
The stealth hypothesis.
The concept of deliberate concealment has emerged as a serious consideration among researchers studying 3I/Atlas, potentially related to dark forest theory implications for interstellar civilizations. Dr. Liu Cixin's theoretical framework, popularized in science fiction but based on real game theory, suggests that advanced civilizations might prefer stealth over open contact to avoid potential threats. Professor Avi Loeb proposes that 3I/Atlas represents what he calls archaeological reconnaissance, a method for studying planetary systems while maintaining the cover of natural phenomena. This hypothesis explains why the object exhibits just enough anomalous behavior to suggest artificiality to careful observers while maintaining plausible deniability as a natural comet. Dr. Jacob Haq Misra from the Blue Marble Space Institute has studied the implications of such stealth strategies, noting that advanced civilizations might prefer observation over contact to minimize risks while gathering intelligence about other worlds. The stealth hypothesis suggests that 3I/Atlas could be collecting data about Earth's technological level, atmospheric composition, and artificial electromagnetic signatures while appearing to be a routine interstellar visitor. Radio telescope monitoring by Dr. Sophia Sheikh at the SETI Institute has detected no obvious artificial signals, but sophisticated probes might use communication methods undetectable by current technology or transmit data during periods when Earth-based observations are impossible.
Lessons from Oumuamua.
The scientific community's handling of Oumuamua in 2017 provides crucial context for evaluating 3I/Atlas and the importance of maintaining open-minded investigation. Dr. Robert Warwick, who discovered both objects, admits that we missed significant opportunities with Oumuamua by dismissing anomalies too quickly rather than pursuing thorough investigation. The 2017 visitor exhibited unexplained acceleration, unusual reflectivity, and extreme elongation that were initially attributed to natural causes without adequate investigation. Professor Abraham Loeb's controversial artificial origin hypothesis for Oumuamua was largely dismissed by the astronomical establishment, yet alternative natural explanations have proven increasingly problematic under scrutiny. Dr. Daryl Seligman's hydrogen iceberg theory requires formation conditions so exotic they approach the implausible, highlighting the difficulty of finding natural explanations for truly anomalous objects. 3I/Atlas represents a second chance to properly investigate an interstellar visitor with advanced instruments and sufficient observation time. Dr. Thomas Zurbuchen, former NASA Associate Administrator, emphasized that extraordinary phenomena deserve extraordinary investigation, not extraordinary dismissal. The lesson from Oumuamua is clear. When faced with genuinely anomalous objects, the scientific community must resist the temptation to force natural explanations and instead pursue comprehensive investigation that considers all possibilities, including those that challenge our current understanding of what's possible in the universe. 3i/Atlas continues its journey through our solar system, carrying secrets that may fundamentally challenge our understanding of what travels between the stars. Whether it's an exotic natural phenomenon or something more extraordinary, this mysterious visitor has already forced astronomers to confront uncomfortable questions about the universe around us. The patterns are too precise, the timing too convenient, and the behavior too strange to dismiss easily. Subscribe to Stellar Tech for more investigations into cosmic mysteries that blur the line between natural phenomena and something far more intriguing. For decades, we've looked at the moon as the final milestone of a bygone era, a silent gray world covered in dust and craters. But the age of lunar stagnation is over. China's ambitious space program has sent back not just rocks, but a technological revelation, a discovery that reboots our entire understanding of the moon's potential and sparks a new technological race to our celestial doorstep. This isn't just about exploration, it's about the technology that will define our future off-world. Let's power up and explore the details. Anomalous lunar structures. The modern debate about strange objects on the moon was largely ignited by the declassified data from the 1994 Clementine mission. This was a unique partnership between NASA and the United States Department of Defense, designed to space test advanced sensor and imaging technology by putting it through its paces mapping the moon. While it achieved its technical objectives, the 1.8 million images it returned have been scrutinized for decades for more than just their scientific value. On the moon's far side, a region permanently shielded from our view, some of these images contain features that appear to challenge natural formation theories. Analysts point to formations with strikingly geometric properties and what seem to be the remnants of large broken-down structures. The most cited example is a feature that has been dubbed the pyramid due to its seemingly flat sides and sharp angular peak. The official scientific explanation is that these are simply visual illusions created by a combination of low sun angles, complex geology, and digital compression artifacts from early imaging technology. However, critics argue that specific sections of these images exhibit unusual blurring, suggesting a deliberate attempt to obscure sensitive data, and that the mission's true purpose was a technological reconnaissance of something unexpected. Ancient astronaut connections. The speculation around lunar anomalies is a key pillar of the ancient astronaut hypothesis, which reframes ancient history as a record of human interaction with advanced extraterrestrial technology. This theory examines old myths and artifacts, searching for descriptions of what might be advanced engineering. A famous, though thoroughly debunked piece of lore is the alleged secret audio from Apollo 11, where Neil Armstrong supposedly describes seeing alien spacecraft. While untrue, it fuels the narrative. This perspective reinterprets ancient texts, like the Sumerian tablets' description of the Anunnaki gods. When a deity instructs his son to wear an eagle's mask for a lunar journey, theorists don't see mythology, they see a technical manual describing a breathing helmet. This technological reinterpretation is applied to artifacts worldwide, including the Wandjina cave paintings in Australia. The figures depicted with their large dark eyes and halo-like helmets are seen not as spirits but as visitors in advanced environmental suits. The theory asks a compelling question: if an early human saw an astronaut today, would they draw a god or a person in a machine? China's groundbreaking discovery. While theories of ancient tech remain debated, China's space program has delivered undeniable technological triumphs. The Chang'e 5 mission in December 2020 was an engineering marvel of automation and robotics. It executed a precision landing, deployed a sophisticated drilling and scooping mechanism to collect nearly 2 kilograms of lunar material from different depths, and then successfully launched an ascent vehicle from the moon's surface, a feat of remote rocketry. After the precious cargo was returned to Earth, Chinese material scientists made 2 incredible announcements. First, they identified a previously unknown crystal in the samples, naming it Change Site Y. This made China only the 3rd country to discover a new mineral on the moon, showcasing their advanced analytical capabilities. Second, and more importantly, their instruments detected water molecules. This water wasn't in the form of ice but was physically trapped inside microscopic beads of glass that were forged billions of years ago in the intense heat of meteorite impacts. This discovery was a technological game-changer, proving that a vital resource for any off-world operation is far more abundant and accessible than previously thought. Revolutionary implications. The confirmation of widespread water on the moon is honestly the single most important technological enabler for humanity's future in space. It makes the engineering principle known as in situ resource utilization, or ISRU, a viable strategy. For decades, the sheer cost of launching every drop of water and ounce of fuel from Earth's deep gravity made the idea of a permanent lunar base, prohibitively expensive. China's discovery changes that financial and logistical calculus entirely. The lunar soil, or regolith, may hold billions of tons of this trapped water. The technology to extract it is actually pretty straightforward. Robotic rovers could be designed to heat the regolith, releasing the water as vapor to be collected. Now this water can sustain life, but its true value is in what it can be converted into. Using electrolysis powered by solar panels, the water molecules can be split into pure hydrogen and oxygen. These are the two most potent and efficient components of modern chemical rocket fuel. This technology would allow the moon to become a fully self-sufficient industrial outpost and a refueling depot, radically lowering the cost and increasing the payload capacity for missions to Mars and beyond. The Chang'e program evolution. China's success is honestly a case study in methodical, iterative technological development. Their lunar exploration program was designed as a series of increasingly sophisticated engineering challenges, with each mission serving as a testbed for the next. The program began with the Chang'e 1 and Chang'e 2 orbiters, which were essentially advanced robotic surveyors, creating the high-resolution maps needed for all future surface missions. The next phase was proving their landing technology. Chang'e 3 successfully put a lander and the U-2 rover on the surface in 2013. Having mastered landing, they tackled an even greater challenge with Chang'e 4 in 2019, a landing on the far side of the moon. This required an entirely new piece of infrastructure, a dedicated communications relay satellite positioned in a stable orbit beyond the moon to bounce signals back to Earth. With landing and long-range communication perfected, they moved to the final, most complex phase sample return. The Chang'e 5 mission integrated all of these technologies and added several new ones, including a robotic ascent vehicle and an automated orbital rendezvous system. This deliberate, step-by-step evolution of their tech stack is what has propelled China to the forefront of lunar exploration. Resource revolution on the moon. The Chang'e 5 samples have honestly ignited a technological and economic revolution by confirming the moon's status as a treasure trove of 21st century resources. The new mineral, Change Site Y, is a carrier of an isotope called helium-3. Deposited by solar winds over billions of years, helium-3 is incredibly rare on Earth but abundant on the moon. It is the most sought-after fuel for next-generation nuclear fusion reactors. The technology of helium-3 fusion promises to generate vast amounts of clean, safe energy without the long-term radioactive waste of current fission reactors. The technology to mine and process lunar helium-3 could literally power the Earth for centuries. Furthermore, the lunar regolith is a rich source of rare Earth elements, which are the backbone of our modern high-tech world, used in everything from powerful magnets and electric motors to the electronics in our phones and computers. Developing the advanced robotics and automated mining technologies required to extract these resources on the moon would not only fuel a new space economy, but would also provide a secure and environmentally superior alternative to terrestrial mining operations. Future lunar colonization. With the key technological barriers of water, energy, and materials now seemingly solved, the engineering challenge of building a permanent human base on the moon has come into sharp focus. In March 2021, this moved from concept to formal policy, when China and Russia announced a joint initiative to construct the International Lunar Research Station, or ILRS. This project is a plan for a permanent, expandable, and eventually autonomous human outpost at the lunar South Pole. This site is considered prime real estate because its deep craters, permanently shielded from sunlight, are thought to hold vast reserves of water ice. The ILRS will be a testbed for a new generation of technologies, including closed-loop life support systems, advanced radiation shielding, and construction techniques like 3D printing habitats using native lunar regolith. To power this ambitious undertaking, China has announced plans to develop and deploy a powerful nuclear fission reactor on the moon by 2028. a foundational piece of technology that would provide the consistent energy needed for large-scale industrial operations and colonization efforts. Lunar resources, the new gold rush. The scientific confirmation of the moon's resource wealth has kicked off a high-tech gold rush, creating a global race to develop the technologies for lunar mining and resource extraction. The focal point of this competition is the moon's south pole, now viewed as the key to a sustainable off-world presence. This technological race, however, is running ahead of international law. The 1967 Outer Space Treaty is the bedrock of space governance and clearly forbids any nation from claiming sovereignty over the moon. But it was written half a century before the technology for lunar mining was considered viable, and so it is dangerously silent on the legality of extracting and owning celestial resources. This legal ambiguity has created a Wild West environment where the First Nations or private companies that successfully demonstrate the technology to mine the moon could establish a powerful precedent, effectively shaping the economic and legal rules for everyone else. This is driving a frantic pace of innovation in robotics, remote sensing, and automated processing, as the finish line isn't just a scientific discovery, but the establishment of a technological foothold. International Space Race. The 21st century space race is defined by competing technological philosophies. The United States is pursuing its return to the moon through NASA's Artemis program, which is structured as a massive public-private partnership. This model outsources the development of critical hardware to innovative commercial companies. For example, NASA has tasked SpaceX with developing its reusable Starship Super Heavy rocket as the primary human landing system, and Blue Origin is building a competing lander. This strategy is designed to accelerate innovation and drive down costs by harnessing the competitive power of the commercial market. This approach is diplomatically extended through the Artemis Accords, an international framework that promotes shared principles for peaceful and transparent space exploration among its many signatory nations. This model of commercially driven, alliance-based development stands in stark contrast to the state-funded, vertically integrated approach of its primary competitors, setting the stage for a fascinating race between two different models of technological progress. Competition between China, US, and other nations. The new lunar race is solidifying into distinct technological blocks. On one side is the US-led Artemis Accords, a large coalition of nations pooling resources and adhering to a common set of operational standards. On the other is the strategic partnership between China and Russia, focused on the development of their joint lunar base, the ILRS, which is building its own coalition of international partners. But this is not merely a two-sided competition. Other nations are rapidly developing their own advanced space technologies and becoming major independent players. In 2023, India's space agency, ISRO, executed a flawless robotic landing with its Chandrayaan-3 mission, becoming the first country in history to successfully touch down near the lunar South Pole. This achievement demonstrated a mastery of advanced autonomous landing systems and put India at the forefront of the search for lunar water. This multipolar landscape, filled with competing government programs and disruptive private companies, is creating an ecosystem of rapid technological advancement. The immense engineering challenges ahead mean that while competition is the current driver, collaboration may be the ultimate key to success. The moon is no longer a distant monument to past glories. It is an active lab, a resource-rich frontier, and the essential technological proving ground for our multiplanetary future. China's discoveries have served as a catalyst, accelerating a new global race to develop the technologies that will allow us to live and work on another world. What piece of technology do you think is most critical for building a lunar base? Let us know your thoughts in the comments. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the stellar tech that is shaping our future. Thanks for watching Stellar Tech. Deep beneath Jupiter's swirling clouds, where crushing pressure should destroy any organized structure, the Juno spacecraft has discovered something that really defies the laws of planetary science. April 18, 2024, marked the day our understanding of gas giants was turned upside down, when Juno's instruments penetrated deeper than ever before and found a massive organized storm system thriving in conditions that should be, well, impossible. This terrifying discovery beneath Jupiter's surface has forced scientists to question everything they thought they knew about how giant planets work, and what secrets they're hiding in their depths.
The mysterious central storm discovery.
Buried beneath Jupiter's Great Red Spot lies something that has left planetary scientists honestly speechless. Juno's microwave radiometer, capable of penetrating hundreds of kilometers below the visible cloud layers, revealed a massive cyclonic structure extending far deeper than any storm system should theoretically survive. Scott Bolton, Juno's principal investigator at the Southwest Research Institute, described the discovery as completely unprecedented in planetary science. The hidden storm system spans approximately 3,000 kilometers in diameter and extends at least 500 kilometers below Jupiter's ammonia cloud deck, depths where the crushing pressure should have destroyed any organized weather pattern. Unlike surface storms that dissipate when they lose energy, this deep structure appears to be feeding off Jupiter's internal heat source, creating a perpetual motion system that may have existed for centuries or even millennia. The discovery really challenges fundamental assumptions about atmospheric dynamics on gas giant planets. Traditional models predicted that Jupiter's atmosphere would become increasingly uniform with depth, but Juno's data reveals complex, organized structures persisting in regions where chaos should reign supreme. This finding suggests Jupiter's interior is far more dynamic and mysterious than anyone imagined.
The beginning of the mission.
August 5, 2011 marked the beginning of humanity's most ambitious journey to Jupiter, when Juno launched from Cape Canaveral aboard an Atlas V rocket. The mission was conceived by Scott Bolton and his team to answer fundamental questions about Jupiter's formation, composition, and internal structure that had puzzled scientists for decades. Unlike previous Jupiter missions that conducted brief flybys, Juno was designed for an extended orbital campaign using a highly elliptical 53.5-day orbit that would repeatedly dive close to the planet's cloud tops. The spacecraft carried 9 sophisticated instruments, including a gravity science experiment that would map Jupiter's interior mass distribution with, honestly, unprecedented precision. Juno's journey required a complex 5-year trajectory, including a crucial Earth flyby in October 2013, to gain the velocity needed to reach Jupiter. The mission faced numerous technical challenges, including designing electronics capable of surviving Jupiter's intense radiation environment, radiation levels that would kill an unprotected human in minutes. NASA engineers had to shield Juno's sensitive instruments inside a titanium vault to prevent radiation damage during the planned 37 orbital passes around the gas giant.
Jupiter is the world of chaos.
Jupiter's atmosphere represents controlled chaos on a scale that just dwarfs anything found elsewhere in the solar system. Juno's JunoCam and infrared instruments revealed that Jupiter's iconic bands and zones are far more turbulent and violent than telescopic observations from Earth had suggested. Wind speeds reach 640 kilometers per hour at the equator, driven by the planet's rapid 9.9-hour rotation period that creates the fastest day of any planet in our solar system. The atmospheric bands aren't static features, but dynamic rivers of gas flowing in opposite directions, creating massive shear zones where adjacent streams collide and generate enormous cyclonic storms. Candace Hansen-Koharchek, who leads JunoCam operations at the Planetary Science Institute, described Jupiter's weather as organized chaos, where small disturbances can cascade into great red spot-sized storms within weeks. The planet's atmosphere extends thousands of kilometers deep, gradually transitioning from gas to liquid hydrogen under increasing pressure and temperature. Juno's microwave radiometer detected ammonia concentrations varying dramatically with depth and latitude, suggesting complex convection patterns that transport material between atmospheric layers. This chaotic mixing prevents Jupiter from achieving thermal equilibrium, maintaining the temperature and pressure gradients that drive its perpetual storm systems across the planet's entire hemisphere.
Io, the volcanic moon.
Io, Jupiter's innermost large moon, represents the most volcanically active world in the solar system, with over 400 active volcanoes spewing sulfur compounds hundreds of kilometers into space. Juno's extended mission has provided, honestly, just unprecedented views of Io's volcanic activity, revealing eruptions that, really dwarf anything on Earth. The moon's extreme volcanism results from tidal heating caused by Jupiter's immense gravitational pull and orbital resonances with Europa and Ganymede. As Io orbits Jupiter every 1.77 days, these gravitational forces flex and stretch the moon's interior, generating enough heat to keep its core molten despite its small size. Alessandro Mura, from Italy's National Institute for Astrophysics, used Juno's infrared spectrometer to track individual volcanic plumes, and discovered that some eruptions reach temperatures exceeding 1,800 degrees Celsius, hot enough to melt rock instantaneously. The volcanic activity continuously resurfaces Io, making it the youngest-looking world in the solar system with no impact craters visible on its sulfur-painted surface. Io's volcanism also feeds Jupiter's radiation belts, creating a plasma torus of charged particles that contributes to the planet's deadly radiation environment that threatens any spacecraft venturing too close.
Research on Jupiter's magnetic field.
Jupiter possesses the most powerful magnetic field in the solar system, extending millions of kilometers into space and trapping deadly radiation that would be lethal to unprotected astronauts. Juno's magnetometer, led by Jack Connerly from NASA Goddard Space Flight Center, revealed that Jupiter's magnetic field is far more complex and honestly chaotic than Earth's relatively orderly dipolar field. The magnetic field strength reaches 4.3 Gauss at Jupiter's cloud tops, 10 times stronger than Earth's field, and is generated by electrical currents flowing through the planet's metallic hydrogen core. Unlike Earth's magnetic field, which has clear north and south poles, Jupiter's field shows irregular patterns with multiple magnetic anomalies scattered across its surface. The field appears to be generated by convection in Jupiter's outer core, where liquid metallic hydrogen acts as an electrical conductor under extreme pressure and temperature conditions. Juno's measurements revealed that the magnetic field varies significantly between different regions of the planet, suggesting complex dynamics within Jupiter's deep interior. The magnetic field creates Jupiter's enormous magnetosphere, which extends beyond the orbit of Saturn and acts as a natural particle accelerator, energizing charged particles to deadly levels that pose serious radiation hazards to spacecraft and future human exploration missions.
Juno mission peaks under Jupiter's surface.
Juno's gravity science experiment has, really revolutionized our understanding of Jupiter's internal structure by measuring tiny variations in the spacecraft's orbital velocity as it passes over different regions of the planet. Luciano Ies, from Sapienza University of Rome, led the gravity investigation that revealed Jupiter's core is not the solid, well-defined sphere that scientists expected, but rather a fuzzy or dilute core extending halfway to the planet's surface. The core appears to be partially dissolved, mixed with surrounding metallic hydrogen, in a way that creates a gradual transition rather than a sharp boundary. This discovery suggests that Jupiter experienced a giant impact early in its formation that disrupted its original core structure. The gravity measurements also revealed that Jupiter's atmospheric bands extend 3,000 kilometers deep into the planet, much deeper than theoretical models predicted. Yohai Kaspi from the Weizmann Institute of Science used Juno's gravity data to create three-dimensional maps showing how mass is distributed within Jupiter's interior. These measurements required extraordinary precision, detecting changes in Juno's velocity as small as 0.01 millimeters per second, equivalent to measuring the speed of a growing human fingernail from millions of kilometers away.
Jupiter's formation and composition.
Jupiter's formation story has been, completely rewritten based on Juno's discoveries about the planet's internal structure and composition. The traditional core accretion model suggested Jupiter formed when a solid core of rock and ice grew large enough to gravitationally capture the surrounding solar nebula gas. However, Juno's detection of a dilute core suggests a more violent formation process, involving planetary collisions that disrupted the original solid core. Tristan Guillot from the Côte d'Azur Observatory actually proposed that Jupiter may have experienced multiple giant impacts during its early formation, including collisions with Earth-sized protoplanets that scattered core material throughout the interior. The planet's composition reveals it contains between 2 and 4 times more heavy elements than the Sun, indicating Jupiter formed from materials enriched in rocks and metals beyond simple gas capture. Juno's measurements show that Jupiter's atmosphere contains water vapor at concentrations of 0.25%, which is 3 times more than previously detected, suggesting the planet formed farther from the Sun, where water ice was abundant. And the discovery of ammonia and hydrogen sulfide at varying depths indicates complex chemical processes occurring within Jupiter's interior, where extreme pressure and temperature create conditions unlike anywhere else in the solar system.
Jupiter as Earth's protector.
Jupiter serves as our solar system's cosmic vacuum cleaner, using its immense gravitational field to capture or deflect potentially dangerous asteroids and comets that might otherwise threaten Earth. With a mass 318 times greater than Earth's, Jupiter's gravity dominates the outer solar system and has fundamentally shaped the architecture of our planetary neighborhood. Kevin Grazier, a planetary scientist who has studied Jupiter's protective role, estimates that Jupiter reduces the impact rate of long-period comets on Earth by a factor of 1,000. The planet's gravitational influence created the Kirkwood gaps in the asteroid belt, regions where asteroids just can't maintain stable orbits due to resonances with Jupiter's 11.8-year orbital period. However, Jupiter's protection isn't absolute. The same gravitational forces that deflect some objects can also redirect others toward the inner solar system. The Shoemaker-Levy 9 comet impact back in 1994 really demonstrated Jupiter's role as a cosmic target, absorbing impacts that might otherwise threaten terrestrial planets. Juno's extended observations have revealed how Jupiter's magnetosphere interacts with the solar wind, creating a protective bubble that helps shield the inner solar system from high-energy cosmic radiation that could affect planetary atmospheres and potentially harm life.
The Great Red Spot Mystery.
The Great Red Spot, Jupiter's most famous feature, has been continuously observed for over 350 years, making it the longest-lived storm system known in the solar system. Juno's close-up observations revealed that this massive anticyclone extends approximately 300 kilometers below Jupiter's cloud tops and reaches temperatures of -160 degrees Celsius at its summit. Amy Simon from NASA Goddard Space Flight Center has tracked the Great Red Spot's gradual shrinkage over the past century. The storm has decreased from 40,000 kilometers wide in the 1800s to approximately 16,000 kilometers today. Juno's microwave radiometer detected that the Great Red Spot is deeply rooted in Jupiter's atmosphere, functioning as a high-pressure system that rotates counterclockwise every 6 Earth days. The storm's iconic red coloration likely results from phosphorus compounds and other chemicals brought up from Jupiter's deeper atmospheric layers through powerful convection currents. Gerald Eichstadt, a citizen scientist working with JunoCam data, has created detailed maps showing how the Great Red Spot interacts with surrounding cloud bands and smaller storm systems. The storm's longevity results from Jupiter's lack of solid surface features or continents that would disrupt its circulation patterns, allowing it to persist indefinitely in the planet's fluid atmosphere.
Jupiter's deep atmospheric layers.
Beneath Jupiter's visible cloud decks lies a complex atmospheric structure that extends thousands of kilometers into the planet's interior, gradually transitioning from gas to liquid under increasing pressure. Juno's microwave radiometer has penetrated deeper into Jupiter's atmosphere than any previous instrument, revealing ammonia concentrations that vary dramatically with depth and latitude in patterns that really defy simple atmospheric models. Chung Lee from the University of California, Berkeley discovered that ammonia becomes depleted at certain depths, suggesting complex chemical processes and circulation patterns that transport materials between atmospheric layers. The atmospheric layers include distinct regions: the upper troposphere where visible clouds form, the deeper stratosphere where temperatures increase with altitude, and the thermosphere where solar radiation heats the thin gas to over 1,000 degrees Celsius. Lee Fletcher from the University of Leicester used Juno's infrared observations to map temperature variations that reveal convection cells extending hundreds of kilometers below the cloud tops. The deep atmosphere shows evidence of phosphine gas, carbon monoxide, and methane that really shouldn't exist at those depths according to chemical equilibrium models. These discoveries suggest that Jupiter's deep atmosphere is actively mixed by powerful convection currents that transport chemicals from the hot interior to the cold upper atmosphere, creating a dynamic system that continues to challenge our understanding of giant planet atmospheric dynamics. Juno's deep scan of Jupiter has revealed a world far more complex and mysterious than anyone imagined. From the dilute core that defies formation theories to the organized storm systems lurking beneath the clouds, Jupiter continues surprising scientists with each new discovery. The gas giant's protective role in our solar system and its extreme atmospheric dynamics make it both fascinating and honestly, kind of terrifying. These revelations prove that even after centuries of observation, Jupiter still holds secrets that could reshape our understanding of planetary science. Subscribe to Stellar Tech for more incredible discoveries from the frontiers of space exploration.